Welcome to the Deep Dive. Today we're getting into something pretty profound, often called the closest thing math has to a grand unified theory. It's the Langlands program.
Mm-hmm.
And this isn't just about, connecting a few dots here and there. It's more like uncovering this deep hidden structure that ties together huge parts of mathematics that honestly looked completely unrelated before.
That's right. Think of it almost like a Rosetta Stone for mathematics connecting numbers, geometry, analysis.
A Rosetta Stone, I like that.
It is. And our mission really in this deep dive is to unpack some of that, to look at this really intricate framework and see why it's seen as this powerful connector. It's about finding this incredible harmony where, maybe we thought there was just chaos before.
Right. And it's wild that this massive, ambitious program basically started from, a letter.
Yes, a rather famous letter now.
From Robert Langlands, a Canadian mathematician, back in, 1967? He's quite young, actually, a professor at Princeton.
Only 30, yes.
And he writes this 17-page handwritten letter to another giant, Andre Weil. And apparently Langlands was incredibly humble about it.
He was. He basically said, read this as pure speculation, or feel free to just toss it. He suggested Ryle might want to have a wastebasket handy.
Amazing. And yet that letter basically laid out the blueprint for, decades of research. It fundamentally shifted things.
Absolutely. And what caught people's attention right away, what was so astonishing, was this ability the program seemed to have. It could take these problems that seemed completely impossible in one area of math and translate them, sort of shift them into a different mathematical language, a different domain. And over there, suddenly they look different, maybe even solvable with the tools they already had.
Like cracking a code almost. Finding the right key unlocks it.
Precisely. It wasn't just theoretical. It had this practical power. It opened up ways to actually solve problems that were just stuck before. Huge classes of problems, in fact.
Okay, let's unpack this then.
Yeah.
How? How does this program actually manage such a massive goal, this unification? What's the core idea?
Well, what's really fascinating, fundamentally, is that the Langlands program is all about finding these deep, often very unexpected connections, correspondences. Think of it maybe like discovering hidden bridges connecting completely separate continents of mathematics.
Okay.
Maybe a simple analogy. Think about natural numbers. 1, 2, 3.
Sure, counting things.
Right. You can introduce them by counting pencils, 1 pencil, 2 pencils. Very concrete. Number theory, right? But there's another way. Imagine winding, say, dental floss around your finger. 1 wrap, 2 wraps, 3 wraps.
Okay, I see where this is going. Topology.
Exactly. That's topology, the study of shapes, windings. And notice this winding way, it naturally brings in positive and negative numbers, doesn't it? Wind clockwise for positive, counterclockwise for negative.
Right. You get direction built in.
Precisely. So the same basic idea, numbers, pops up naturally from counting, which is number theory, and from winding, which is topology. Two seemingly totally different starting points.
And the Langlands program is essentially looking for those kinds of deeper connections on a much grander scale.
That's the big picture, yes. It aims to build these bridges between number theory, geometry, and another crucial area of LA is a theory of automorphic forms, finding the underlying unity.
Right. This is where it gets really interesting, isn't it? Let's maybe dig into those foundational pillars. You mentioned number theory and something called the local global principle.
Indeed. Number theory, for a very long time, has been obsessed with finding integer solutions to polynomial equations.
Like Fermat's last theorem.
Exactly like Fermat's last theorem. Does xn plus yn as en have whole number solutions when n is bigger than 2? Turns out, no non-trivial ones. The local global principle offers a different angle on problems like this. It suggests that sometimes a global problem like finding integer solutions can be understood, maybe even solved, by looking at it locally.
Locally meaning? What exactly?
Locally means looking at the problem in simpler number systems, like solutions modulo m, so looking at remainders when you divide by m, and also, crucially, in what we call p-adic numbers.
Okay, hold on. P-adic numbers. That sounds abstract. Could you give us a feel for those?
Sure. They're a bit weird at first glance. Think of them as a completely different way of measuring the size or distance between numbers. Instead of how far apart they are on the number line, you measure based on divisibility by a specific prime number.
So not based on magnitude, but on prime factors.
Essentially, yes. It's like putting on special glasses that only see multiples of, say, 3 or 7. Kurt Hensel formalized this back around 1897. And the idea is sometimes if you can solve your equation in all these different p-adic worlds for every prime pia.
You can piece together a solution in our regular global world of integers or rational numbers.
That's the hope. It's like solving a jigsaw puzzle. You solve lots of small local pieces and hope they fit together to give you the big picture.
And does it always work?
No, that's the catch. It doesn't always work. But when it does, it's incredibly powerful. The Hesse-Minkowski theorem is the classic example where it does work beautifully.
Right. The Hesse-Minkowski theorem, what does that say?
It deals with a specific type of equation called quadratic forms. And it says, basically, that such an equation has a solution in rational numbers, that's the global part, if and only if it has solutions in the real numbers and in the p-adic numbers for every single prime p.
So for those equations, the local picture completely determines the global one.
Exactly.
Yeah.
Solve it everywhere locally, and you've solved it globally.
And then there are these things called adeles and adeles.
Yeah.
How do they fit in? You said they help make things more symmetric.
Yes, adeles and adeles are, well, they're clever mathematical constructions. Think of them as a way to bundle all these local pictures together. They allow mathematicians to treat all the places, all the different p-adic worlds for every prime p, plus the real numbers, which we sometimes call the infinite prime, simultaneously on an equal footing.
So it's like creating a single framework that holds all the local information.
Precisely. It gives you a unified way to talk about the local properties everywhere at once. It's a crucial technical tool for making this whole local global approach systematic and powerful.
Okay, that makes sense, a unified viewpoint.
Yeah.
So moving on from number theory, the program also relies heavily on automorphic forms and L functions. What are automorphic forms?
Right. Automorphic forms are generalizations of functions with very special symmetries. The simplest example is like the sine function, it repeats every two parts.
It's periodic.
Exactly. Automorphic forms are like that, but they have much more complex symmetries. They automorph, they transform back into themselves under a whole group of transformations, not just simple shifts. Think twists, reflections, things like that.
And they have links to number theory.
Oh, absolutely. Their importance for arithmetic was spotted way back in the 19th century. Jacobi used related functions, theta functions, to get formulas about sums of squares around 1830. And Riemann, about 30 years later, used similar ideas for his famous zeta function, understanding its properties.
And Erich Heck was important here too.
Very much so. Heck figured out how to characterize automorphic forms using something called their associated Dirichlet series. This was key. It showed that these symmetric functions were popping up, as he put it, everywhere in number theory. They explain symmetries hidden in number sequences, and L functions are deeply tied into this.
L functions, they generalize the Riemann zeta function, right?
They do. L functions are fundamental analytic objects in the Langlands program. They generalize the zeta function, Dirichlet L series, and others. A key feature they often have is an Euler product expansion.
What's significant about that? An Euler product?
An Euler product is like a fingerprint for the L function, built purely from prime numbers. It decomposes the function into an infinite product involving just the primes. Having one tells you the function encodes deep information about prime numbers. And crucially, the Langlands program predicts that L functions coming from number theory via Galois representations, which we'll get to, should match L functions coming from these symmetric automorphic forms.
So the L function is another part of this bridge, connecting different areas.
Exactly. It's often the L function that explicitly makes the connection.
Okay, so that brings us to the third pillar, Galois representations and reciprocity. What role do they play?
Galois representations are, think of them as ways to capture the symmetries of number systems. They encode really deep arithmetic information about how numbers behave when you extend a number field, like adding the square root of -1 to the rational numbers.
So they capture structure and symmetry?
Precisely. They're like sophisticated maps of the algebraic landscape.
Mm-hmm.
And from these representations, you can build certain L functions called Artin L functions. And now we get to Langlands' really big conjecture. Conjecture 1, it's audacious. It basically says that every Artin L function coming from an n-dimensional Galois representation is actually the same as an L function coming from some suitable automorphic representation on a related group, GLN.
Wow. So the L functions from the number theory side, Galois, are predicted to be exactly the same as L functions from the analysis symmetry side, automorphic forms.
Exactly the same. It's proposing a dictionary, a direct translation between these two worlds that looked completely separate before. This generalizes a known result called Artin's reciprocity law, but takes it vastly further.
That really does sound like a Rosetta Stone, translating between fundamentally different mathematical languages.
That's the core idea.
So, okay, this is obviously huge within pure mathematics.
Yeah.
But what about outside? You mentioned connections to physics, computer science. How does something this abstract connect there? Let's start with physics.
Well, the connections to physics are quite profound, actually. Things like gauge theory, string theory, they are deeply concerned with symmetries, just like the Langlands program. Symmetries are fundamental to how we describe particles and forces.
So it's the shared focus on symmetry.
That's a big part of it, but it goes deeper. The Langlands program seems to resonate with a concept in physics called duality.
Duality.
Duality is this amazing idea where two physical theories, which look completely different on the surface, turn out to be mathematically equivalent, describing the same reality from different perspectives.
Like electric-magnetic duality.
Exactly, or strong-weak coupling duality in quantum field theory, even things like high-low temperature duality in statistical models like the Ising model. The Langlands program seems to provide a mathematical backbone for understanding some of these dualities.
That's fascinating. So it's not just math mirroring physics, but maybe providing the underlying structure in physical phenomena.
It appears that way in some cases. It also shows up in descriptions of the quantum Hall effect, both integer and fractional, and it's connected to Chern-Simons theory and conformal field theory, CFT.
And didn't the physicist Edward Witten work on this?
He did. Witten, a Fields medalist himself for his work in physics, got very interested in the geometric version of the Langlands program. He brought powerful ideas from quantum field theory, especially CFT, to bear on it, revealing even deeper connections.
Incredible. Okay, what about computer science? The links seems less obvious there.
It's perhaps more indirect, but still significant. For example, parts of the Langlands program connect to algebraic geometry over finite fields.
Okay.
And that area of math is crucial for creating powerful error-correcting codes. You know, the codes that make sure data transmits correctly over noisy channels or on CDs and DVDs.
Ah, I see. So the underlying math finds practical application.
Exactly. And also, the number theory side of Langlands is related to understanding prime numbers and factorization. Improving algorithms for factoring large numbers is, of course, very important for cryptography and security.
Right, because breaking encryption often relies on factoring.
Precisely. So advances spurred by Langlands-related ideas could indirectly impact cybersecurity.
And you mentioned quantum computation, too.
Yes, there are links emerging there as well, particularly in topological quantum computation. This is an approach that hopes to use exotic quasi-particles called anyons and their braiding properties, how they move around each other to perform quantum calculations.
Braiding, like literal braids.
Mathematically, yes.
Yeah.
The theory involves things called braid groups, Jones polynomials. Very topological ideas. The abstract structures studied in parts of the Langlands program seem relevant to describing these anyons and their potential for computation. There are also connections to quantum annealing, which is a type of quantum computing aimed at solving optimization problems.
So the reach is really broad, even if sometimes indirect.
It really is.
Okay, so the program's been around since the late 60s. It's clearly still very active. What's been happening recently? Any major breakthroughs?
Oh, absolutely. There was a truly monumental development just very recently. In July 2024,
Yeah.
a team led by Dennis Gatescory and Sam Raskin announced a proof of a major part of the geometric Langlands conjecture.
The geometric version.
Yes, there's a parallel version of the program cast in the language of algebraic geometry rather than number theory. This proof was the result of, well, something like 30 years of intense effort.
30 years. How big was the proof?
Over 800 pages spread across 5 papers. It's a colossal piece of work.
Wow. So what does that mean, proving part of the geometric conjecture?
It means they've essentially settled a key piece of the puzzle in that geometric column of this mathematical Rosetta Stone. It's a landmark achievement. Now, it's important to say it doesn't solve everything. Even in the geometric world, things like the local theory or quantum geometric Langlands are still very much open quadrants. But it's a huge step forward.
That's incredible. Are there other new approaches being developed, too? I saw mention of something called the Langlands Watch framework.
Yes, the LW framework. That's quite a different novel approach. It focuses specifically on elliptic curves, which are central objects in number theory.
Elliptic curves, right?
Yeah.
Connected to Fermat's last theorem proof.
Exactly. The LW framework uses this intriguing time-inspired analogy. It talks about a second hand, a minute hand, and an hour hand associated with the elliptic curve.
With a clock.
metaphorically. These hands are mathematical objects designed to capture information about the curve's arithmetic properties at different scales, both locally and globally, dynamically reflecting the curve's symmetries.
And what's the goal of looking at it this way?
The main goal is to get a finer handle on some really hard problems about elliptic curves, particularly the Burton-Swinnerton-Dyer conjecture, the BSD conjecture.
One of the Clay Millennium Prize problems, right?
That's the one. The LW framework aims to refine predictions about the rank of an elliptic curve, which sort of measures how many rational solutions it has, and also about this mysterious thing called the Tate-Shafarevich group, which measures, roughly, the failure of the local global principle for elliptic curves.
So it's a new tool aimed at very specific, very difficult problems.
Yes, and it's designed in a way that might be generalizable beyond elliptic curves, too, which is promising.
Okay, so we have geometric progress, new frameworks.
Okay.
But you mentioned earlier that the absolute core of the original Langlands program, this idea called functoriality, is still unsolved.
That's right. Functoriality remains the heart of the matter, the really central, overarching conjecture that ties everything together, and it's still open.
What makes it so important and so hard?
Its importance is hard to overstate. If functoriality is true, it would imply so many other things. It predicts how automorphic forms should transform into new automorphic forms under certain operations. Proving it would automatically lead to proofs of other major conjectures, like the Ramanujan conjectures about the size of coefficients of certain modular forms.
So it's like a master key that unlocks many other doors.
You could say that. Its truth has also had unexpected historical consequences already. Andrew Wiles's proof of Fermat's last theorem actually relied on proving a special case of Langlands' functoriality, a connection that apparently surprised Langlands himself.
Really? Even he didn't see that connection coming.
So the story goes, it just shows how deep and interconnected these ideas are, sometimes in ways even the originator didn't fully anticipate. Functoriality remains the grand challenge.
So wrapping this up, the Langlands program, it really is this, as you said, fathomless and mysterious landscape, but clearly central to modern mathematics.
Absolutely. It's a synthesis of major themes from classical number theory. It's a roadmap for future research, and it really acts as this grand unifying framework.
Unifying number theory, geometry analysis, with ripples going out into physics, computer science.
That's right. And despite the huge progress, like the recent geometric proof and these new ideas like Langlands watch, there's still so many open questions, these deep mysteries, these core conjectures like functoriality still waiting.
It's a living, breathing field of research.
Very much so. It constantly reminds us that the deeper we probe into the fundamental structures of mathematics, the more surprising and beautiful connections we tend to find.
So maybe a final thought for our listeners. With these recent breakthroughs, the geometric proof, the LW framework, how might these developments finally light the way towards tackling that ultimate challenge of functoriality? And what other unexpected dualities or connections, maybe between math and physics, might this program reveal next?
Those are exactly the kinds of questions driving the research. The journey continues.